Hello everyone, welcome back to Bites of CC. So this lecture is about batch normalization. So before we know what a batch normalization is or what the batch normalization does, let's learn about why batch normalization was implemented in the first place. So when we train the neural network, say in case of very deep neural network, what happens is during training, the previous layer's parameters change, and hence the input distribution to the next subsequent layer also change. So this input distribution changes for each and every layer of the neural network. Now that poses a problem because it slows down the training, since the hidden layers need to adapt to this new distribution. This problem is known as the internal covariate shift. Now, in order to tackle or just to make sure that the change in distribution isn't too high, two steps, or two, what shall I say, measures are being taken. First of all, the learning rate is chosen to be very, very low. And next, when the neural network gets started, we need to initialize those weights and biases of each layer. We just initialize that to some random value. So that initialization has to be very carefully done so that the distribution after changing, like after the gradients are being calculated, and the weights and biases are updated, it doesn't differ too much. But that gives rise to two very difficult problems. One is the convergence is really, really slow. Sometimes they can't even converge to the global optimum, like the global minima or the global maxima. And another very, very notoriously difficult problem that arises is to train models with saturating nonlinearity. Now, what is a saturating nonlinearity? So, saturating non-linearity is basically a function that bounds the input to some fixed bounded interval, and whenever the input exceeds this interval, the output is a constant. Now, a typical example of this can be a sigmoid function or a hyperbolic tan function. And if you study those established neural networks, you will see that most of the times developers don't tend to use the sigmoid or tan h as their preferred activation functions. And this is one of the reasons why these functions are carefully avoided. So ReLU is usually the preferred choice of designers who are designing a very deep neural network, like say Tacotron. So now a proper solution to this kind of a problem is to normalize the layer inputs. Now, what happens in batch normalization is we fix the mean and variances of layer inputs, which improves the training speed. Now, what is meant by fixing mean and variance of layer input? It means that we fix the mean to 0 and variance to 1. And also the third factor is that the features are to be decorrelated. But this is not a very important thing, not very important, but not that important. So we are not talking about that factor. So we are just concerned about the mean and the variance of layer inputs, and you will know why we are just concerned about mean and variance. And it has also been established in many of the research papers, like this is one of them, but there are also other research papers which have shown that the training speed has greatly improved. The training in general has greatly improved when the mean and the variance have been fixed for the inputs. So this is also known as whitening. So when the inputs are whitened, it also makes it possible to use saturating nonlinearities in your saturating nonlinearity problem is also taken care of when whitening is used. But the problem is when we are using whitening, this process is extremely computationally intensive. And a full whitening also is not everywhere differentiable. So when we are using, like when we are batch normalizing or when we are using this whitening procedure, some simplifications are made to the whitening procedure. Number one, instead of whitening the features in layer inputs and outputs jointly, each scalar feature is normalized to have zero mean and unit variance. So, since we are very used to seeing tabular data, so in your tabular data, instead of normalizing the entire row, what we do is we normalize column wise. So, the feature the features of like this column corresponds to one feature, so this column is normalized and this column is normalized, and so on the normalization process happens. So mathematically, if I have to show you, suppose a layer has d-dimensional activation x. Now, d-dimensional means there are d features, and why are we using this term activation? See, when we are, so for the first layer, it receives, say, some raw input R, and we add some weight to this raw input, like we multiply it with some weight, and we add a bias. So both W and B are trainable. And now, since this is a neural network, and so this affine transformation is made to pass through an activation function, say A, and that produces some output, say, what shall I say, P, and this P is the input to the next layer. So this activation function can be sigmoid, tanh, ReLU, any of these. So basically, we will be dealing with this P, which is more appropriately the, we can call it the activation. This is not the raw input, but the activation. After the weights, biases, and the activation function has been applied on this. So that this P is here basically represented as X. So instead of P, we can actually use X here. So this is the X that we are talking about. So now a layer has d-dimensional activation, so this is represented as x1 to xd. Now for a particular dimension k, that is you can call it the third column, this k can be 1 to d, any of these. It can be normalized as x cap k equals to xk minus expectation of xk. This is you can call it the mean. I show you. This is basically the expectation, that is 1 by n, we sum over xi. So there are, say, n examples or n number of n number of examples in that in your data set, and we add those up and then we divide it by n. So basically we are finding out the mean, and that is divided by root over variance of this xk. So x here is actually xk, okay? This is your xk. And now what happens here is, now when we normalize each input, now this can change what the layer can represent, like, right? So to address this kind of problem, another transformation is done so that we can get back the original activation, that is this xk. What is that? We applied a learn, scale, and shift parameter to the normalized value. Now again, what does that mean? So for a particular dimension k, your gamma k is a scale parameter and beta k is a shift parameter, and we find this yk, which is equivalent to gamma k into xk, hence the name scale parameter, and that is added, and to that is added this shift parameter, that is beta k. Now how do we get back xk from this particular equation? Now if we consider gamma k as root over variance of xk, now we are considering this equation. Now this is your x cap k, And now we say, so gamma k was multiplied with x cap k, right? So gamma k is supposed to be here, and this gamma k is equivalent to root over variance of xk. So numerator and denominator is the same. So this gets cancelled out. So this gamma k, I'm just slowly cancelling out. Okay, gamma k gets cancelled out. Now this, you're left with x cap k. Sorry, not actually x cap k. Actually, you're left with xk minus expectation of xk. So now when you fix beta k to expectation of xk, so xk minus expectation of xk plus expectation of xk. So these expectations get cancelled out and you are left with xk. I hope that hope you could understand this. Now the question is, why are we using this term batch? We are using this term batch because we actually use mini batches in training, and for each mini batch we need to produce this estimates of mean variance of each feature. Now suppose your mini batch contains m training examples. Now this algorithm has been taken straight from the paper which proposed batch normalization by Google researchers. So now here this x is basically xk. For simplicity, they have omitted using this term like k. They've omitted this factor k, but x will mean xk here. Okay, so no confusion. So your input will be values of x over a mini batch b, which is there will be m training examples, so x1 to xm, and there will be parameters to be learned like gamma and beta will also be added as input, and it will output yi for the batch for this particular for this particular input x. So mu b is actually the batch mean or the mini batch mean. So there are m training examples. So I will be summed up from, sorry, x will be summed up from I equals to 1 to m. So x1 plus dot 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 xm divided by, of course, there are m examples, so m. Now this is the variance, which is 1 by m, I equals to 1 to m, xi minus mean, the whole square. Then we need to normalize. So this is just that equation that you had seen, but there is a difference. Now you can see that there is this factor epsilon. Now this epsilon is actually a noise factor which is used to add some numerical stability to the equation. It has been seen that this works as a regularization factor, and definitely it gives better results and helps the network not to actually what shall I say, overfit. And this epsilon is actually taken from a normal distribution. So yes, we also make sure that whenever we add noise to the network, in neural network, make sure that you choose that random value from a normal distribution. And then we calculate yi, just as I had shown just a few moments before. So this is how yi, that is m values of this y's, are actually calculated. Now this is when the training happens, but in case of inferencing, so batch normalization generally uses moving averages of mean and variance which are computed during training rather than using the statistics of the current mini batch, because that again gives you better results. The inputs are more consistent, sorry, the outputs are more consistent and stable. So now let's take an example. Suppose you have an input something like this, because all the inputs are numerical. As you know, when the network takes in the input, those are numerical. There's no categorical values. So I had actually used this particular value and have this is this x represented by this x, and I had made to This is I've used Torch PyTorch framework, sorry, PyTorch library, whatever you call it. So I have made it to pass through the batch normalization, and the output is this. I have just done away with the floating part because I had to use this dtype float because the batch normalization, of course, for valid reason, hasn't been implemented for long or in type of data. So if I just rule out this trading zeros, so if you see here, the batch mean for this particular column was 1.5, and this value is less than the batch mean, and the value after batch normalizing it gets a value of -1, and this was greater than the mean of this particular example, and this gets a value +1. But in this case, since the mean for this particular column is 2.5, so 2 being lesser than that, this gets a value of -1, and this gets a value of, this 3 gets a value of 1. So this is how the particular x input gets normalized. Now, since I have used this, you already know that PyTorch, Keras, all the leading libraries, the very commonly used libraries, have already implemented the batch normalization, so you do not have to implement the code for this. Now, the question is, when do we apply batch normalization? Now, batch normalization is applied after the weights and biases are added and before the activation is applied. So, this code snippet I have taken from Stack Exchange. So, this uses Keras. And now, see, in this sequential model, batch normalization has been used. So, this is the fully connected layer. This is the fully connected layer. Next, we use the batch normalization. Then a hyperbolic tan activation has been used, and finally a dropout has been used. Similarly, for this particular chunk, this is for the hidden layer. Again, this is the fully connected layer, then batch normalization, then activation, and then dropout, and same also for the output chunk. So this is how a batch normalization is applied, and this is also true for PyTorch models also. Now, what are the advantages of batch normalization, which is very important, of course, because why do we use something without knowing what advantages it gives us? First of all, it stabilizes the learning process. So it, when we normalize the inputs, it really stabilizes the process. It reduces the internal covariate shift, and naturally it also accelerates the training, and it also helps you to use higher learning rates now, since the inputs have been normalized or whitened, whatever you call it. What happens here is, when we use a higher learning rate, the convergence is also faster, and also we do not have to overtly dependent on how to initialize your model, because of the same reason, because it is normalized. Now you do not have to think much about the internal covariate shift that a particular initialization can lead to. Then since we have used that epsilon parameter, as you have seen in the original algorithm, it also helps reduce the overfitting, and the gradient flow is also improved in this case, because the gradients now have more consistent magnitudes, and the vanishing and exploding gradients are the issues that we normally face. These are also taken care of using this normalization technique. Now, this was used again by the original paper, so they trained the network. So they trained using on the MNIST data set. So they trained without using batch normalization, which is shown using this dotted line, and they also used batch normalization to train the network. Now, this is the accuracy, and this is the number of training steps. Now, if you closely watch this, I hope you can watch this, this is clear. or at least you can make out what is meant, what is shown over here. So I can consider this point when the this dotted line, or the network without batch normalization has converged. Now if I draw a line here, you will find out that it took almost 25,000 training steps to converge to the solution. Whereas if I consider this training which was done using batch normalization, see from the initial iterations, like the initial results was more than zero point 0.9. It was like, what would I say, 0.95 or something in the graph, probably something like that. So when it started from, I think 7.23 whatever, whereas this started from 0.95 or 0.94 whatever, something like this. And by, I would say this might be the point. So before 20,000 iterations, I think probably this would be 16,000, 17,000, whatever. It has already converged. So 25,000 versus I think 15 or 16,000. So that's a big improvement. And this is the input distribution graph without using batch normalization. And this is the input distribution graph by you after using batch normalization. So this is a more stable, consistent, and a better, of course, a better distribution. This is a better graph, of course. Everybody would agree to that, right? So this naturally proves that batch normalization makes the distribution more stable, and hence it reduces the internal covariate shift. So that is all about the basics of batch normalization. So that's all for today. Thank you for watching.